Hello, in this video we're talking about the equations of motion, or you might affectionately know them as the suvat equations. We're going to talk about kinematics equations. How do you do some math to find like velocity, acceleration, displacement, time, all those things based on each other when you know a few. So here we go. Okay, the equations of motion, the suvat equations, are ones that you do need to know a very specific rule for. There's a big assumption, limitation, stipulation of these equations, which says they work for uniform acceleration. They only work for uniform acceleration. That is when you have a constant acceleration. This can be, this can cause a little bit of trouble just because everybody loves suvat so much, and you just always want to suvat everything. You see something with like a velocity, and you maybe we'll jump right to suvat. But if there's a changing acceleration, which would come from, say, a changing like net force situation, you can't use these equations. So you have to have a constant acceleration throughout like the duration of the problem that you're looking at for these to work. So one big example, kind of the main example, and the main example where this comes up and is a little sticky too, is free fall. So free fall is a great example of a time when you have constant acceleration, and you would have constant acceleration because free fall is defined as, an object is in free fall if the gravitational force, the force due to gravity, is the only force acting on the object. All right, so if it doesn't just mean something falling through the air, this means we have to be able to convincingly ignore air resistance, which we usually can unless the problem tells us not to. All right, so if you're in free fall, you can use these equations because your acceleration will be like negative g, negative 9.8-ish, negative 10-ish meters per second squared. Okay, but you can't use this if the acceleration changes. So one of the big times where this comes up when you're using the suvat equations, the equations of motion, is something like this. The classic problem, stand on the edge of a cliff and toss a stone up into the air and watch it go, fall down, and splash into the sea below. That good old one. A lot of times you might be tempted to start this problem and say initial speed is 0 because it starts like in the person's hand and is not moving. Well, you can't do that. That will not work because the equations will only work when the acceleration is g, which means while it's in the air. The equation will only work while the stone is in the air. So we would need to make, like in this example, the initial speed would be 13 meters per second. We can't say it like starts from rest because then we're dealing with a force from the person's hand and the force due to gravity. And if there's any change to the force situation, there's going to be a change to acceleration, and you can't use suvat. So for this kind of example, you would, your initial speed, and we'll get into all these, but your initial speed would be the speed that it like is thrown into the air with. So again, here 13 meters per second would be the initial speed in our equation, because we're going to tell the equation, tell me what happens when the thing starts moving up this fast and the acceleration is g. Yeah, and then the final speed is also not 0. You can't be like, oh, it hits the ocean or the ground or whatever and then stops, so final speed is 0, because then the net force situation is changing too. You have a force like from the ground or from the air or something. Okay, so free fall is a big time we use suvat, and we're using free fall. It only works while it's in the air, not while it's being thrown or started or stopping at the very end or anything like that. All right, so that's the big like limitation to keep in mind and conceptually think about when you're doing the math to guide your physics brain. Okay. What if, though, you have a non-constant acceleration? Well, the IB might make you deal with it just a little bit. One place, and we've probably looked at this a little bit already, is like with motion graphs. You can definitely talk about motion graphs where your acceleration is a changing value and talk about what that looks like on a velocity graph and fun things like this. All right. You can't use the suvat equations, and you won't really do much math when there's a changing acceleration. The one thing they might get into is this very fun idea that just like we have all of our different rates of change, right? There is a rate of change called a jerk. And a jerk is officially the gradient of acceleration. It's how acceleration changes with time. All right, you can keep doing rates of change forever, and this is really true. It's amazing. Physicists are so fun when they come up with names. So, your rate of change of displacement is called velocity. Your rate of change of velocity is called acceleration. Your rate of change of acceleration is called the jerk. And guess what? You can also do a rate of change of a jerk, and that's a snap. And the next one's crackle, and the next one's pop. That's what they decided to name them. All right, so fun. So that's the definition of a jerk. Again, the IB has said they might give you some non-uniform acceleration situations. So if they do, and also in the rare case that they ask about a jerk or just like the rate of change of acceleration, you would just do this like you do for all the other ones. Like when we do, velocity is delta S over delta T. You could do slope of a tangent line on an S versus T graph. Or find like an initial and final displacement and an initial and final time. Assuming this is like a straight line, and you can do it that way. Yeah. So anyway, it's probably not going to come up very much, if at all, but they have said you might deal with some changing acceleration situations. So just so you know, that's called the jerk, and you'll probably do it on motion graphs. You maybe will do a simple rate of change like this. Okay, but outside of that, let's talk about our good old kinematics equations when you do have a constant acceleration. So we'll real quick kind of show where these come from because it might help to understand what's happening. So we're saying these equations work when there's a uniform constant acceleration. We can derive this from picturing a velocity versus time graph. Because if I have a constant acceleration, well, what is acceleration in terms of velocity? Well, remember, acceleration is the rate of change, the gradient, really, of velocity. And so acceleration would be the slope of a line at any given point, at least. It'd be the slope of a line on a velocity versus time graph. Since it's a constant acceleration, it's going to be a straight line, like a non-changing slope, right? The gradient of this graph doesn't change. It stays the same steepness. In other words, it's a straight line. Okay, so this is what my velocity versus time graph would look like. And what we can do then is use a linear equation. We're just gonna write an equation with a linear form because that's what we got. Like kind of by definition, if acceleration is constant, a velocity graph will be linear. So how would we do this? We do good old y equals mx plus b. Now, whenever you're looking at a graph in physics, you want to combine, your math and physics knowledge. So y equals mx plus b. Great classic math right there, right? You want to translate that to what's on the graph because it's not math class. It's y means something, x means something, right? We're representing physical quantities here. So what is represented by y? Well, I would say y is velocity, right? So this we can replace with a variable to represent the velocity of the object at any given point in time. What's on x? Well, time is on x. So we're going to kind of write our linear equation. We'll do one step at a time here. We would say v. This really, we can write an equation where, if you like, v is a function of t. Yeah, I get a certain velocity for any given times. This tells me how velocity depends on time. It has something to do with this slope and something to do with b, the y-intercept. Okay, well, we know the slope is a, right? That's the definition of acceleration. It's the gradient of v versus t graph, and so it would be the slope of this straight line. So the slope of this graph is a, so we're going to call this guy a instead of m, the generic math slope. It actually means something, so we'll call it a. And so does this, right? B, the y-intercept. So there's your y-intercept. I think we know how to find it on a graph. Do you remember the definition from math of a y-intercept? Because it's not like where it crosses the y-axis. That's how you find it. But the definition is it's the value of y when x equals 0. That's what the y-intercept is. Let's put that in physics terms because y is velocity, time is 0. So that's velocity at time t equals 0. So that's my beginning velocity, my initial velocity. And kind of because we already have a v, we're going to, the IB style, and you see this a lot, we're going to use u for initial velocity. All right, u for initial velocity. So put that all together, I get my y value v equals the slope, which is acceleration, times the x value time, plus the starting value, which is we're going to call initial velocity. And just to make it pretty, we're going to flip it around like this, because that's how we typically write it in physics. And look at this. This is our first kinematics equation. You'll see that in the data booklet. All right. There are 3 others. Some of them come from some fun stuff like calculus, which you might learn about someday, but we don't need to worry about that. So here they are. There they are. There's 4 equations of motion that you can use. All right, so take note in these equations of what's vectors and what's not, because the IB doesn't give you this. This is pretty much the equations of motion as they appear in the data booklet, except they don't have any of the vector bars. If you go through the whole data booklet, you'll notice the IB doesn't have vector bars anywhere. They do this on purpose because it's really important, like what's vectors and what's not, but they want you to have that knowledge. They want you to have that physics knowledge. They want you to understand every variable and every equation, what it means, what the context is, how to use them. So you need to know which of these are vectors, which is all of our, motion vector stuff, right? Velocity, acceleration, and displacement are all vectors, whereas like time is not a vector. Time is a scalar. Yeah. So know that these are all vectors, which means direction is going to matter, which we'll see when we practice. Yeah, but there you go. These all give the different kind of quantities in terms of each other. They're really, S and V are really kind of functions of t. So S will tell me what's my displacement after some time t. Yeah, or some time t after the U condition really is what's happening. All right, so use my initial velocity. I need that in all the equations because I got to tell the equation what my starting condition is, and then I can find whatever else I need. A should always be a constant value, right? That's the limitation of these equations. Yeah, and so that's what we use them for. You'll notice there's 4 equations, which is useful. They all will get you to the same place, but you want to kind of solve these in a smart way where you're doing as little work as possible. So you'll notice all of them deal with a different combination of 4 variables. So all of them are missing one of these variables. So you use that when you are choosing one of these equations based on the problem, right? Like this first equation has no A, no acceleration. So if you don't know or care about acceleration, you would probably use this equation. This equation has no S. So if you don't know or care about displacement, you would use this one. This equation has no V. Yeah, no V. So you would use that if you don't know V. And this one has no T. So you could use that if you don't know T. Of course, you could use any of these and do like combinations and substitutions, and they'll all kind of get you to the same place. But the idea is pick the smart one. Okay. Some other quick little tips about solving problems before we look at a few quick examples. The equations are one-dimensional officially. So really you want to think about this as like X stuff and Y stuff. So you're always going to be working either horizontally or vertically, never both at the same time. And that has to do with the way acceleration and net forces kind of work, and the independence of horizontal and vertical motion, which is so fun because gravity's down. Okay, so you're only going to do stuff left to right or up and down, depending on the context of the problem and what you need. Make sure that you're going to use signs. So these are vectors, so we need to assign direction, and our convention is we use plus and minus for direction. So picture your regular Cartesian plane, your XY plane. That's the easiest way to do it. So usually we're going to say positive is to the right, negative is to the left, for example, in a horizontal problem, or positive is up, negative down in a vertical problem. Okay, that's just a sort of convention, though. As long as we're using signs some way or another, we'll always get the same answer and agree. In other words, if I decide to say I'm going to make down positive, it'll work out the same. I might get an answer of positive 10, where you might have said down is negative, and you get an answer of negative 10. Well, we're saying the same thing because we're both saying 10 down. All right. So as you get more used to this and get fancy, you can kind of see some situations where flipping it might be helpful, but for the most part, you'll be perfectly fine if you always say to the right is positive, to the left is negative, up is positive, down is negative in X and Y. When you're dealing with a vertical problem, almost always, like when you have a free fall thing, unless they tell you otherwise, in free fall, when we're near the surface of the Earth, right, unless I give you the weird Mars problem or something, you use the acceleration due to gravity. Little g, our good friend little g. Okay, it's in the data booklet right there, and we're going to use 9.8, just 9.8. It does, this third decimal actually, it does depend on where you are on the Earth. So we're just going to use 9.8. That's plenty good for us. Yeah, so 9.8 meters per second squared is the acceleration due to gravity. Notice they're giving you the magnitude of g, because sometimes you need magnitude, sometimes not. Sometimes you need it as a vector, like here. So when this is acceleration, like when this is the physical acceleration of an object, it's a vector and it's down, right? It's towards Earth's surface, so it points like down towards the ground, officially towards the center of the Earth. Yeah, so we're gonna make that negative in like suvat problems when we use it almost always. Sometimes if there's like a not calculator problem where they ask you to estimate, or if the problem just prompts you, sometimes the IB will just say you can use G as 10. You know, it's close enough when rounding, you're going to be very close to the right answer. But otherwise, use 9.8, grab that calculator, and go from there. Okay, so let's look at some. Let's talk about the process of how to solve these. Okay, the method I'm going to encourage you to use that I think is really great is to make a little table, just like this, a suvat table. Every time you have a problem where you think, oh, okay, there's some suvat happening, I think I want to do an equations of motion thing, you make this right away. You make this little SUVAT so you can list out what you know. Okay, because really everything problem solving in physics kind of boils down to the same strategy, which we can call the guess method for find your givens, find your unknowns, pick an equation that'll work, and then do some substitution and solving. Yeah. Okay, so this will really help us pick the right equation and think about what we know. So here's how we go through this. We got a car moving horizontally at a certain speed, 26.8, suddenly applies the brakes and stops after 2.5 seconds. What is the acceleration of the car during this time? Okay, so we have a couple numbers here, and we want to immediately identify those with variables. We're going to give some physics variables to these. That's the key. So it's moving with the speed of 26.8 meters per second, and then it applies the brakes and stops. This is definitely velocity. It's measured in meters per second. And I really just got to ask myself, is that the initial or final velocity? Yeah, so what do you think? I would say that must be my initial velocity, because it's like what's happening at the beginning, right? And then it stops and does some other stuff. So that's the initial velocity. This problem doesn't exactly spell out which way it's moving, so I'm just going to say this is in the positive direction. So I got my car going somehow this way. Yeah, so I got a beautiful car. Let's make a little sketch. Beautiful car going this way. It's got initial speed of 26.8. It goes some distance and then it stops. So I'm trying to picture what's happening in the problem. All right, I got this 2.5 seconds. That's definitely time, right? And I'm going to start filling these into my table. So I have initial velocity is 26.8 meters per second. I have my time is 2.5 seconds. And they ask me, what is the acceleration of the car? So I'm solving for A. So I like to do something like this. If you're fancy, use a colored pen or something. Right, like this is the thing I'm solving for. I need to solve for A. So the rule with suvat, if you look at the equations and think about how math works, with all those equations, if you know any three of the suvat variables, you can solve for a fourth. So you need to know at least three of these things, S, U, V, A, or T. And once you know three of these things, you're kind of done hunting through the problem and you can solve for the thing you need to solve for with suvat. So I've only got two things that I know super directly from the problem in terms of numbers it gives me. I must be able to figure out something about one of these others, S or V, right? The displacement after time t or the velocity after time t. Well, if I think about it, I'm pretty sure I know that velocity because it stops, right? So, I mean, implied by the problem, but I got to recognize that that means the velocity, the final velocity, if you want, the velocity after 2.5 seconds is 0. So we're going to put in 0 for velocity. Yeah, which means I don't care about S. I don't have to think about it or worry about it at all because there will be an equation using these four variables where I know the three of them and I can solve for A. So I look through my data booklet and I look at those four equations and I say which one does not have an S in it, because that's the one I want to pick, because I want the one where I don't have to worry about S. Well, it's that first one we came up with, V equals U plus AT, classic. Okay, so V equals U plus AT is what I'm going to use. I should always, always, always solve for the variable I want algebraically before I plug in any numbers, because that's good practice and it's going to help me, number one, think and understand conceptually what's going on better, which is the most important part, and number two, make sure I minimize calculator errors, and stuff like that. And it just goes quicker once you get used to it. Okay, so let's solve for A. Let's do some algebra. Solve for A. I'm going to subtract a u from both sides. You can do 2 steps here. And then I'm going to divide both sides by t. So I got v minus u over t equals A. Being careful to keep the things that are vectors vectors. Yeah. And now I've solved. This is really the answer to the problem, to be honest. That's the important answer. That's the physics answer. Now the number is just plugging in some numbers I made up, yeah, and getting some answer, some number, okay? But this is really the important part, if you ask me. All right, so let's plug in. I know v is 0. U was positive 26.8, so I'm going to subtract that. Meters per second, and the time is 2.5 seconds. I punched it in my calculator, and I get a negative answer. I got negative, and I'm going to round to 3 sig figs because I have 3 sig figs in both of my given values. So I'm good with 3 sig figs. I got negative 10.7 meters per second squared. Okay, which makes sense because I defined this velocity to be positive. And so if I have a negative acceleration, that just means my acceleration is to the left, which means that's the direction in which the velocity is changing, right? It's becoming more to the left by becoming less to the right, if you like that. And remember the rule too, that if your velocity and acceleration are in different directions, you slow down. It has nothing to do with the acceleration being negative. It's only because acceleration is negative and velocity is positive that it slows down. Okay. All right, so there you go. That's how you do suvat. Make a little table, go through your equations, and pick the one that makes life easy. Let's look at one more, a vertical one, and see what we come up with. Look at this. Only one number they give us. Holy moly. Well, we must be able to figure it out. Oh, the classic. We throw a stone vertically upwards with the speed of 12 meters per second. Find the maximum height reached by the stone. Oh, boy. All right. Well, they're clearly telling me what to find here. They're asking me to find maximum height. I don't have like an H in these, but I can understand that that means I'm solving for displacement, right? If I find its displacement, its position from 0 after some time, well, I can find them. That would be a height, right? So I'm trying to solve for S, and I'm definitely dealing with like vertical stuff. So this is all, you know, in the Y dimension. So I can kind of think about these being here too. Okay, they give me 12 meters per second. So what should I do with that? Well, a little tricky. Let's maybe sketch this. So I take a stone, I throw it upwards 12 meters per second. And I want to find the maximum height. Right? Yeesh. Okay, I want to find the maximum height. It's going to like go up and then come kind of straight down. I'll draw it a little bit like this to picture just what's happening, right? And I want to find the maximum height. I really want to find this. Yeah, which let's just call it SY at this point. That's what I care about. All right, that 12 meters per second then I'm thinking has to be the initial speed. Again, don't fall into the trap of saying, well, you throw it, so it started at rest in your hand. No, you can't do that because we're going to be dealing with it in the air when we're not pushing it with our hand. Yeah, and so this equation will only work while it's in the air. It's thrown into the air with this speed, so that makes this my initial velocity. It's upward, so it's definitely positive. I'll do this a lot too, just to force myself to remember about vectors. I'll put a little plus before the 12, just to make sure I'm thinking about that. Obviously, that doesn't matter math-wise, but it's kind of good practice just to be thinking in vectors all the time. Okay, the other thing that I know, because it's a vertical problem and we throw it through the air, is I know acceleration, because this is a vertical problem, going to be negative 9.8. It's the acceleration due to gravity, because while it's in the air, gravity is the only force acting. Yeah, so that's a freebie in a vertical problem. I think it's implied here that we're like, you know, on the Earth, so that's what I'm going to use for A. Now, I want to find S, so the question is, can I figure something out about V or T? And I think surely we can, right? Because if I know V or I know T, then I'll have enough to solve for the S that I want. I don't think we know T, and there's not really a good way to find T without first knowing V. So what do? I got to think about what's V up at the top here. And think about it. How fast, for the split second that the stone is up here, how fast is it going? Well, I would say it's at rest. The stone is at rest. Yeah, picture throwing something up in the air. It does momentarily stop right at the top. One way to think about it is right over here, it's going up, and a split second later, it's going down. Well, it must have stopped to turn around, right? To go from positive to negative velocity, it's got to go through zero in the middle. So for that split second, the stone really is at rest there. It is accelerating. It's still got an acceleration of -10, but it's at rest, right? Only for a split second, but that's what we need. So velocity is 0. Yeah, V is 0. Now I'm good to go. I got my 3 numbers and 1 unknown, so a suvat will get me there. Since I, again, in double checking, I got constant acceleration since we're in free fall. So I'm going to pick the equation that doesn't have an s, which is this guy, v squared equals u squared plus 2as. Fantastic. All right, and I'm good to go because there's an s here. I know the 3 other things, so now it's just a math problem. So let's do some math. I'm going to do a couple math steps at once. Let's just get the s by itself. This is perfectly fine in an exam. This is not math class. You don't need to show every step of your algebra. If you are algebra proficient, you can definitely jump right here. Yeah, easy enough to see that we took a u squared away from both sides and then divided by 2a. Yeah. Okay, so let's go ahead and plug in now to find s, because I'm a good physics student. I solved for s before I plugged in any numbers. One exception is you could, if you want to, just put in a 0. Zeros are good ones to plug in right away. That one you can do. But either way, I'm going to get over here. 0 minus, okay, be careful with this, 12 squared, right? I'm still going to subtract because of order of operations. I square the 12, and then I subtract that whole thing from the 0. I'm going to have a negative up there. I'm going to divide by 2 times negative 9.8 meters per second squared. Let me go ahead and keep being a good physics student, and I'll put in units here. It's 12 meters per second that I'm squaring. Okay, so I do this, I get like what, 144 over just under 20. I plug it in my calculator. It's a negative over negative, so I do get a positive, which should make sense. And I have 2 sig figs in the number I'm given, 12 meters per second, so I have to round my answer to 2 sig figs, which is going to get me 7.3 meters. I am checking to make sure that I got a positive answer, because based on the context of the problem, I know that this should be positive, right? It's a positive displacement. Since I'm defining up as positive, down as negative, I need a positive answer. If I got negative 7.3, I missed something. I maybe did order of operations wrong, or forgot to put a negative in front of the 9.8 or whatever. Yeah. And in more complicated problems, mixing the negatives up will give you the wrong number often. So that's really what it comes down to. Be careful with your directions, make a little suvat table, but that's kind of it for suvat. All right, they're so fun. Practice them a little bit, and you will love suvat like all physics students. All right. So there you go. There's suvat. Go practice. Have fun.